At a quick glance, these two molecules look like they could be twins. But you know, in the world of chemistry, even the tiniest difference in structure can lead to a massive difference in personality. So today, we're going to dive into the story of alcohols and phenols and see how one little change creates two completely different chemical playbooks.
All right, here's our game plan. We'll start with our two key players and what makes them tick. Then, we'll open up the standard toolkit for changing alcohols. After that, we're going to switch gears completely to phenols and see why their reactive ring is such a game changer, which leads to some really famous high-impact reactions. And finally, we'll wrap it all up with the key takeaways.
Okay, let's meet our main characters, alcohols and phenols. What they have in common is this really powerful and versatile little thing called a hydroxyl group, or OH group. But where that group is located, well, that makes all the difference in the world. So you can see it right there, that OH group is the core similarity. But in chemistry, your neighborhood, it really matters. In an alcohol, the OH is just hanging out on a simple carbon chain. But in a phenol, it's attached directly to this special, super stable structure called a benzene ring. And that single connection, that is the source of all their differences. So, let's zoom in on alcohols first. You should think of them as these awesome, versatile starting materials. Chemists have this whole toolkit of reactions they can use to turn them into all sorts of other useful molecules.
The first tool in the box is oxidation. You can think of it as a controlled way of adding more oxygen bonds. But the final product you end up with depends entirely on two things: what kind of alcohol you start with and the specific chemical tool, the oxidizing agent that you decide to use.
And this table really lays out the strategic choices you have. If you've got a primary alcohol, a mild tool gives you an aldehyde. But if you hit it with a strong one, you push that reaction all the way to a carboxylic acid. Now, secondary alcohols, they're much more straightforward. They always oxidize to a ketone. And tertiary alcohols, well, because of their structure, they just kind of sit there and refuse to oxidize under these conditions.
Of course, there's always more than one way to get the job done. Chemists can use specialized recipes like the Swern oxidation, or a more physical method, like just passing the alcohol vapor over some hot copper. But check out this clever little twist with tertiary alcohols. Instead of oxidizing, that hot copper makes them lose a water molecule, forming a totally different kind of compound called an alkene. Pretty neat, right?
All right, let's move on to a reaction that creates some of nature's most pleasant smells. It's called esterification, and it's how we make esters, the very compounds that are often responsible for the sweet smells of fruits and flowers. The recipe is a total classic. You just combine an alcohol and a carboxylic acid with a little bit of acid to get things moving. What you're basically doing is pulling a water molecule out from between them, and that lets the two bigger pieces link together to form the ester. It's just a simple, really elegant way to build bigger molecules. Our final tool for alcohols is dehydration. And yeah, it's literally removing water. By heating an alcohol with a strong acid, we can basically force the OH group and a hydrogen next door to leave as a water molecule. When they pop off, the carbon atoms they left behind form a new, stronger double bond between them, creating a molecule called an alkene. So here's how it works, step by step. First, the acid makes the OH group a much better leaving group. It basically turns it into a stable water molecule. Once that water leaves, you're left with this temporary positively charged carbon atom. We call that a carbocation. This thing is unstable, so it quickly fixes itself by kicking out a nearby hydrogen, which lets that new double bond form. That stable carbocation pathway is exactly what makes this reaction so easy for tertiary alcohols. But what happens if there's more than one spot where that double bond could form? Well, chemistry tends to prefer the path of least resistance, and that's all summarized by Seitzeff's rule. The reaction will almost always make the most stable product possible. In this case, that's the double bond that's surrounded by the most other carbon groups. At the end of the day, nature favors stability. Okay, let's switch over to our other molecule and see how that benzene ring changes absolutely everything. For phenols, the main story isn't about what happens at the OH group itself, but about how that group completely changes the behavior of the entire ring it's attached to. This right here, this is the single most important idea for understanding phenols. That oxygen atom in the hydroxyl group actually donates some of its electron density right into the benzene ring. This makes the ring electron-rich and basically supercharges it, making it way more attractive to other chemical groups looking for electrons. So not only does the OH group supercharge the ring, it also acts like a traffic cop. It tells any new group exactly where to attach. And the spots are very specific, either right next door, at the ortho positions, or directly across the ring at the para position. It is incredibly precise. And here's the proof in the pudding. When we react phenol with nitric acid, that new nitro group doesn't just stick on randomly. Nope, it follows the rules, and you get a mixture of two specific products. One where the group is next door, at the ortho position, and another where it's directly across, at the para position, just like the traffic cop predicted. And if you want to see the true raw power of this activation, wow, just watch what happens with bromine. The reaction is so fast and so powerful that it doesn't just add one bromine atom, it adds three, one to every single available ortho and para spot, and it happens instantly, creating this solid white product. It's a really dramatic way to see just how much influence that -OH group has. Okay, now for a couple of the celebrity reactions. These take advantage of phenol's unique reactivity to create incredibly specific and useful molecules. I guarantee every chemistry student learns these by name. First up is the Kolbe reaction. The strategy here is just brilliant. Step 1, you make the phenol even more reactive with sodium hydroxide. Step 2, you bring in carbon dioxide, which adds a new carbon group to the ring. And step 3, you add acid to finalize the structure, and what you get is your product, salicylic acid.
And this is why this reaction is so famous. That final product, salicylic acid, is the essential starting material that's used to make one of the most common medicines on the entire planet, aspirin. It is a perfect example of how these fundamental chemical rules lead directly to products that impact all of our daily lives.
Our second famous reaction is the Reimer-Tiemann reaction. This is another really precise tool, but this time its job is to add a completely different kind of group, an aldehyde group, or CHO, onto that phenol ring. The reaction uses chloroform and sodium hydroxide to get this done, and it specifically adds that new group right at the ortho position. So, after exploring their unique chemical personalities, let's wrap this all up. Let's put our two building blocks, alcohols and phenols, side by side one last time to really hammer home the key differences.
So let's just boil it all down. For alcohols, the chemistry happens at the OH group itself. That's where the action is, where bonds are broken and formed. But for phenols, the OH group is more like a conductor, directing all the action to happen on the benzene ring. It's a totally fundamental difference in where the reactivity actually is.
You know, at the end of the day, structure dictates function. These two toolkits, one for alcohols, one for phenols, are the foundation for creating everything from fragrances to medicines. Understanding which tool to use and where to use it, well, that's the art of chemistry. And the next time you see some complex molecule, you can bet that somewhere in its creation, these fundamental rules played a starring role.